Why are large graph databases hard to scale? Have you ever wondered why large graph databases can be so challenging to scale? Let's break down the reasons behind this complexity in a way that's easy to understand. First off, large graph databases contain millions to billions of nodes. Which are the entities and edges? Which are the relationships between those entities? As the size of the graph increases, the number of relationships per node also grows. This leads to a situation where storage and retrieval of data become more demanding. When you run queries that need to traverse many relationships, they can slow down significantly if they are not optimized. Next, let's talk about distributed storage and graph partitioning. To scale a graph database, data is often spread across multiple servers or clusters. However, splitting a graph into parts can be tricky. Relationships often span across these partitions, which means that queries that need to access data from different partitions can become costly in terms of performance. This can lead to slow query responses and increased communication overhead. Another challenge is the complexity of graph queries. Unlike traditional databases that may use simple key-value lookups, graph queries often involve multiple hops and complex patterns. This requires more computation and memory. When dealing with large datasets, ensuring that these queries run efficiently without timing out or using too many resources is a real challenge. Moreover, many graph databases do not have mature indexing or caching mechanisms. This means that when you try to filter data based on multiple properties of nodes or edges, performance can take a hit, especially as the size of the graph grows. Integration with existing systems adds another layer of difficulty. Many businesses use relational databases alongside graph databases. Synchronizing data and queries between these systems can complicate matters. Migrating large datasets or running queries that span both types of databases requires careful management to avoid inconsistencies and slowdowns. Lastly, consider the hardware and infrastructure needed for large graph databases. Storing and processing these extensive graphs requires significant memory, central processing unit power, and fast input-output operations. Without the right infrastructure, transactions can take a long time or even fail to complete. From a backend development perspective, these challenges mean that designing scalable graph database solutions requires thoughtful planning. Developers need to think about how to partition data, optimize queries, and integrate graph databases with other data stores. They also have to keep an eye on performance and adjust system resources to handle the workload effectively. In practice, large graph databases work best in scenarios where relationships are key, like recommendation engines or social networks. However, scaling these systems involves trade-offs and often requires a combination of graph databases with traditional databases to strike the right balance between performance and functionality. Understanding these challenges can help developers create more robust systems that effectively utilize graph databases.